In this lesson, we're going to be looking at the graphs for exponential growth functions. In general, when we talk about an exponential function, we're looking at an equation of the form y equals a times b to the power x. What's really key to note here is that your exponent is x, which that's why the whole function is called an exponential function. We've never really messed around with an equation where the input is an actual exponent. Now, there's different parts to this function, and the first of which is that leading coefficient, the a value. In general, the a value can be anything except for 0. The b value, or the base of the exponent, is going to be any positive number, and it cannot be equal to 1. And you might be able to think of why that is, but we can talk about it tomorrow in class. What I'm going to really kind of focus for in this particular lesson is the following. For this lesson, we're going to be looking at a values that are bigger than 0 and b values that are greater than 1. And if that happens, y equals a times b to the x is called exponential growth. So, what we're going to do right now is graph a very basic exponential growth function and really kind of analyze it thoroughly. So, example 1, let's graph the following. Let's graph y equals 2 to the power x. Now, just to kind of relate it back to this formula, you might be wondering, well, I don't see an a value there. All I kind of see is the base for my exponent 2. So you might be kind of considering that this b is 2, and you would be totally right. To figure out the a value, consider I can rewrite this if I wanted as y equals 1 times 2 to the power x. That's still just 2 to the x. So it's not written there, but the a value is 1. So that'll be kind of useful as we move forward. To graph this, at least for the first time, I'm going to make a table of values, and I'm going to make a bunch of values. Let's start off with plugging in 0. If I plug in 0, I get 2 to the 0 power. Now, some students think that is 0, but you have to recall that anything raised to the 0 power is really just 1. Now, if I plug in 1, I get 2 to the first. That's easy. That's just 2. If I plug in 2, I'd get 2 to the second, which is 4. If I plug in 3, that's 2 to the third, and that would be 8, not 6. And so on it goes. This thing grows exponentially, so it grows very, very fast. We can plug in negatives. Now, if I do 2 to the negative 1, I have a lot of students that will write that as negative 2, but in fact, if you remember negative exponents, all that means is you have to put it into the denominator and it will become a positive 1. So it's really just 1/2. If the exponent is negative 2, it would be 2 to the negative 2 power, and I get 1 over 2 squared, which is 1 over 4. And so on and so forth it goes. Now you might be thinking well, what if I plug in negative 10? Maybe, this thing will become an actual negative number. But not so. If you do 2 to the negative 10, all that does is move the base downstairs to have a positive exponent. 1 divided by 2 to the power 10 is super, super close to 0. I think it's like 1 over 1024 or something like that. So it's like almost 0. But you'll never quite get there. And we'll kind of talk about that a little bit as we graph this thing. Now, as we put down this graph, we're going to plot these coordinates. So when I plug in 0, remember we got 1. When I plugged in 1, I got 2. When I plugged in 2, we got 4. And when we plugged in 3 over here, we would get out 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it grows pretty quickly. And when we plugged in negative 1, we got half. Should be about right there. Then we got a fourth, and then an eighth, these points, as I go further and further to the left, never quite touch the x-axis. They get super, super, super close. In fact, you can get as close to 0 as you want the further left you go, but you'll never quite touch 0. As you move to the right, this thing grows very fast, actually grows exponentially. I should probably have continued that to hit the point I plotted there. So it grows exponentially. Let's talk about a couple things. First, I would make sure you remember this image. This is what an exponential growth curve looks like. All right. When we talk about our domain for such a thing, there's nothing you're not allowed to plug in for x. You can plug in positives or negatives. It really doesn't matter. So we can say all reals. And for the range, well, the range doesn't give you every single y output. If you think about it, the lowest y value you can get is really close to 0, but not equal to 0. So we're going to say all outputs, or y values, are going to be strictly greater than 0 for this curve. I'm going to do one more example with you. Let's call this example 2. I'm going to graph y equals negative 3 to the power of x. Well, here I can rewrite this if I wanted as y equals negative 1 times a positive 3 to the x power. So my a value is negative 1 and my b value is 3. Oops. Now, if you'll notice, this is not exponential growth, because for exponential growth, that a value has to be positive. So right away, this is not exponential growth. So I'm already keeping in mind that I'm not going to get a picture like that. Okay? Let's see what does happen by filling out a table. Now, in general, guys, I'm going to be happy if you guys just fill in like 3 coordinates. And usually the 3 coordinates I like to plot are when I plug in 0, so it'd be negative 3 to the 0 power. Now, only the 3 is being raised to the 0, and there's a negative 1 in front, so it's really like negative 1 times a 3 to the 0, which is just negative 1 times 1, or negative 1. Now, you'll hopefully get pretty fast at that. You won't have to write out all those steps. If I plug in 1, it'll be negative 1 times 3 to the first, which is just negative 1 times 3, which is negative 3. If I plugged in negative 1, and these are the 3 x values I think you're going to want to plug in here. 0, 1, and negative 1. Those are like kind of the easiest ones. If I plug in negative 1, it's going to be negative 1 times 3 to the negative 1, which, remember, this negative exponent just means bring this guy downstairs. So it's negative 1 in front of the fraction 1 over 3 to the positive first. So negative 1 times 1/3 is negative 1/3. Now, let's make a graph of this. When I plot 0, negative 1, that's going to be right about here. And when we plugged in 1, remember we got negative 3. So negative 1, 2, 3, that would be right there. And when I plugged in negative 1, I got negative 1/3. Now, something very similar happens. As you plug in negatives, this will get closer and closer and closer to the y-axis, or excuse me, the x-axis, but never quite touch it. It gets as close as you want to 0, but it never quite gets there. As I move to the right, it moves downwards and falls off very quickly, much the same way our graph over here grew exponentially very fast. Our graph over here falls off in the same manner. As a matter of fact, these two graphs are related. They're kind of like reflections of one another. The only problem is the base I changed to a 3 instead of a 2. So when we talk about this kind of graph, we can look at the domain, and notice we could still plug in all real numbers. It doesn't really matter what I want to plug in. I can put in all reals, and my range, instead of being all y values greater than 0, the largest y value I can get is just really, really close to 0, but it's still negative. So in this case, my domain is all y values less than 0. Now, what I'd like you guys to try is the following. See if you can graph this coming into class. you try two graphs. A, see if you can graph y equals 3 to the x power. And for B, see if you can graph y equals -2 times 2 to the x power, and see how that goes. And we'll go over it tomorrow. Thanks for watching.